I'm Nikos Katsouris from the EVENFLOW project, and I will briefly talk about the work that we're doing on robust learning and reasoning for complex event forecasting and the relation of that to some aspects of trustworthy AI. So, in in one sentence, EVENFLOW's mission is to develop scalable, formally verifiable, and explainable neurosymbolic techniques for detecting imminent critical situations before they actually occur. So this last part is what complex event forecasting refers to. And these situations very often are known and they are defined by domain experts via temporal patterns of symbolic nature, while at the same time on the input side, we have streams of sub-symbolic input, like for example, streams of images or video or high dimensional time series. And so this is where neurosymbolic techniques come in an effort to combine sub-symbolic input with symbolic knowledge. And moreover, we want our methods to be applicable and safely deployable to mission critical and safety critical applications. So that's why we're focusing on them being formally verifiable. And of course, since scalability is of paramount importance here, due to the temporal nature of these applications and the requirements for fast response times and low latency and stuff like that. So we're working on scalability techniques for neural training, neurosymbolic training, and scalable verification. We have three use cases in the project. The first one is on personalized medicine, and the goal here is to forecast events related to the disease progression, and in particular cancer, breast cancer. So the approach that we follow is that we harvest gene expression data from real patients from open databases, and we use them as training data on generative AI techniques in order to generate virtual patients. This is necessary due to the lack of sufficient real data. And then we probably combine these virtual patients over time to generate patient trajectories, which correspond to views of disease progression. And then we try to extract temporal patterns from these trajectories and use them for forecasting deterioration conditions. The second use case is about Industry 4.0. The goal here is the main focus is safe and reliable robot navigation in smart factories. We have data from automated guided vehicle robots perception modules, also symbolic knowledge from the robots execution plans and their mobility patterns, and we use them to build event forecasting models in order to make collision or delay forecasts in a decentralized fashion. The third use case is about infrastructure maintenance. Here we're working with water pipe accelerometer data obtained from sensors inside the pipes, in addition to spatial knowledge about the network topology, and we're trying to build models for localized leakage prediction. So let me go a little bit in more detail regarding one of these cases, the robot use case, in order to be able to talk about the aspects of trustworthiness that we're touching upon in EVENFLOW. So we have, as I said, automated guided vehicle robots moving around the smart factory floor. And we want to develop forecasting models, event forecasting models, which can be used by each robot individually in order to timely detect collisions or delays due to obstacles. And these forecasts then can in principle be used by the robots to dynamically adjust their course to avoid these unwanted incidents. So we're working with perceptual input obtained from the robot's onboard cameras, so what the robots see at each point in time. And at the same time, we have symbolic knowledge on the other side, which is either given domain knowledge, like the high-level execution plan that each robot is associated with, or symbolic knowledge that can be learned from event logs of previous robot execution, like, for example, mobility patterns. And we use neurosymbolic techniques to jointly train vision models from the perceptual input with the knowledge. And then we use the probabilistic semantics of these models to derive forecasting models based on standard Markov chain theory, which allows to to cast forecasting as prediction of the likelihood of a pattern completion in the near future. So the aspects of trustworthiness here is, of course, first of all, temporal neurosymbolic learning and reasoning, which is a set, an arsenal of techniques uh, towards trustworthy AI, mostly because of their they allow for more interpretable techniques and the alignment of perception with domain knowledge and constraints. So we are also working on formally verifiable models. So the point here is to assess whether the neurosymbolic forecasting model is robust to input perturbations. And crucially here, we're not just addressing the neural components of the entire model, which can be done with standard neural network verification techniques, but instead we are concerned with the robustness of the entire system as a whole. So from input perturbations to the robustness of the vision models in the slides example here, to the robustness of the actual reasoning-based forecasts, temporal reasoning-based forecasts of the entire system. And then there's explainable forecasting. So we're working with techniques that can offer explanations to domain experts for the forecasts in terms, for example, of what is the most likely sequence of future events that may cause a particular forecast to be emitted. And on top of this, in EVENFLOW, we think that the very capability of event forecasting in event-based applications is something that can pave the way towards trustworthy AI. It can increase the trustworthiness of the entire system, precisely because we can use this forecast to take proactive corrective measures to avoid unwanted situations or to take advantage of situations and things like that. So regarding the future, I'm touching upon here just one category of systems, which is of AI systems, which are of interest in EVENFLOW. Of course, it is a very broad category of systems. It subsumes many applications. And these are systems that combine learning from perception level experience and reasoning with what has been learned, plus domain knowledge, and doing that over time. So systems that can learn and reason while planning, adapting their behavior, things like that. So one example is autonomous systems, of course. There are many other examples of systems with increased trustworthiness requirements, like, for instance, medical decision support systems and things like that. And there are two main points regarding trustworthiness here, in my view. The first is that, of course, such systems need to be explainable in order to be understand and debug their decisions and their inner workings. And also, they need to be reliably robust and safe in order to be usable in high-stakes applications where probably they're needed the most. And the point here is that due to the fact that they combine modules of different nature that span almost the entire arsenal of AI techniques like reasoning, learning, planning, things like that. So modular and compound approaches, like, for example, neurosymbolic techniques are promising here for reasons related to the fact that they have more interpretable behavior. They allow for better error and failure containment and localization. And also they allow to enforce functional specifications related to properties of correctness, safety, fairness, and so on via dedicated training techniques. And also they can be made to be fully verifiable end-to-end. Of course, there are many fronts regarding research. You can see them on the slide. And with that, I conclude. Thank you very much. You can learn more by visiting our website. Thank you.